Hi, Dave here again for a quick one. This is the benchmarks directory in my Adaptive Radix Tree project. Last few videos we were walking the radix tree and making an intermediate result that logically represented a massive regex patterns. One for the unique words in Moby Dick, another one for the unique words in Shakespeare, and we um, walked those intermediate results to serialize them into actual regex pattern strings, and we tested them out. It was a lot of fun. Now, obviously, one of the big ways of solving regex patterns is by using state machines. Not all engines do that, but it's a popular way to solve regex patterns is by using non-deterministic finite automata or state machines. And I thought, how fun would it be to compile massive diagrams of these state machines? And so I did. And so I have a massive 44 megabyte NFA state machine diagram for the Moby Dick regex pattern and another one for the Complete Works of Shakespeare words. Before I show you them, I just want to give you a little bit of a peek into what the compilation logic looks like. So the start of this is the same as usual. You know, we're tokenizing the text and inserting all the words into the radix tree, and then we get the intermediate result by calling that toRegex function. And then there's one thing that I do a little bit differently, and you see this class and branch sequence. So last time, we kind of needed, when we're kind of serializing it, we need to figure out when we're iterating through these groups in the intermediate result, these group arrays, whether or not two adjacent entries in the array are separated by concatenation or alternation, those two operators in regex. And we did that by doing kind of a weird approach, analyzing the last token in the output array to orient ourselves. We needed something more robust for this, so I came up with this class branch sequence, which will group those the byte stacks and the groups that are actually concatenated. And so at the beginning, I actually just do this right here is a recursive depth first traversal, right, of those in order to figure that out. In order to kind of reduce those groups and the intermediate result into. Anyways, other than that, it's just a standard depth first traversal of the intermediate result to produce the output rules, and I'll show you what the rules actually look like. So the library that I'm using is called GraphViz. I tried Mermaid.js, but number one, it doesn't work on ARM64 processors, so using it in Termux or Userland or even a Raspberry Pi doesn't work. I originally wrote the script to use it, and I set it off on my gaming laptop, and it ran for at least 6 or 7 hours and still wasn't finishing. And in that time, I researched GraphViz and tried GraphViz on my phone, and it finished the Moby Dick SVG on my phone. So I went with GraphViz. It's a faster library. Now, this is what the command file looks like. The way that I'm doing it is these libraries that render SVGs from these state machine commands like this, each node, right, you have like, that's how state machines work. You have one node, and then you have another node, and then a transition between them. It's like a graph, right? And so each node or vertex needs an ID. And so the way that I did it is very natural for a trie-style NFA or trie-style state machine. Each vertex or node, its ID is the hexadecimal encoded prefix of to that point in the tree. And so that's what these X followed by numbers are. Those are node IDs. And then the arrow means a transition, and then the label is the label of the transition. Okay. And so it's pretty big, but that's basically how it works. So let's go back, and I will show you what the Moby Dick diagram actually looks like. So I'm going to click on this, and it'll take a minute to load. So it's 44 megabytes for the Moby Dick SVG. It's 66 megabytes for the Shakespeare SVG. Even GraphViz, you can tell that it's not a linear or sublinear algorithm, that somehow even GraphViz is a superlinear algorithm, because it took a little more than an hour for the Moby Dick SVG to finish on Termux on my phone, and it took well over 4 hours for the Shakespeare one, even though it's not twice the size. So also, these are extreme aspect ratios. So the aspect ratio of the Moby Dick NFA is 1 by 307, which means that if I physically printed this NFA state machine diagram, and this is a big one, if I printed it out on a long banner that was 1 foot tall, that banner would be longer than a football field. And the Shakespeare one, which I'm going to show you in a minute, you can see you can just keep going and going and going because of that extreme aspect ratio. The Shakespeare one is 1 by 328, which is something like, on a 1 foot tall banner would be like 1 1/4 football fields or something like that. Or no, not 1/4 football fields, but pretty long, right? So football field in like 25 or 28 feet or something. Anyways, an American football field is. Yeah, so I mean, really, really kind of difficult to get a full picture of, in any one medium, but this is it. It's really cool. So that's the Moby Dick one. I'll show you the Shakespeare SVG. And the fact that they have such a wide aspect ratio, it's a testament to the advantage of this type of data structure, right? The advantage is that, as you keep adding additional words to the try or the NFA, the data structure, because it's a try-style approach, right? It primarily, these data structures, they grow sideways, right? They don't get taller when you add more stuff. There are other, this is the Shakespeare one. There are other data structures that are not like that. Binary search trees, for example, they do get taller as you add more and more things. Not in a linear scale, they like logarithmically, but still the height does grow. These don't. The only way that these data structures get taller and taller is if you put longer and longer words or longer and longer text in them. So, and then you can just keep scrolling and scrolling and scrolling. Yeah, so this was compiled with GraphViz and my radix tree. So, anyways, thanks for watching.